Welcome to this NPTEL course on Microhydrodynamics. My name is Anubhab. I'm an associate professor here at the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Microhydrodynamics deals with the world of very viscous flows. You might already be interested in problems in viscous flows without actually formally thinking about it, and these arise in both the built and the natural world. You could be curious about what is responsible for the growth of raindrops inside clouds, or the formation of the spray in the ocean, or the ash that is spewed out of volcanoes. You could be interested in questions regarding what makes a colloid stable, or how do paints spread smoothly. What is responsible for the flow of material like powders and granular material. In the biological context, you might be thinking about how do bacteria swim? Are they any different from how we swim at a very large scale and scale? How do cells move around in blood vessels? Or for that matter, how any pathogen is basically getting transported through our mucus in the respiratory airways. All of these processes are governed by the physics of slow, viscous, highly resistive flows. So welcome to the fascinating world of low Reynolds number hydrodynamics. At such small scales, inertia no longer matters. Be a dust particle, a droplet, a bacterium, none of these are coasting along when you give them a push. They almost stop instantly. This is the realm where viscosity dominates and the physics is governed by the Stokes equation, which is beautifully linear and reversible. In this online course on microhydrodynamics, we would be exploring this resistive world. When a particle moves through a viscous fluid, it is dragging the fluid along with it. When two particles are interacting, the motion of one affects the other. Be thin filaments, drops, bubbles, microorganisms, all of them are governed by the equations of highly viscous flows. The techniques you will learn in this course come straight from the modern toolkit of fluid mechanics. The exact solutions of Stokes' equation, flow singularities, Faxon's laws, methods of reflection for doing hydrodynamic interaction, or even when you are very close to each other using a lubrication theory. You will understand that when we have deviations from the viscous world and we account for weak effects of inertia, how does that completely alter the flow topology? We'll also be exploring that if we are accounting for the inertia of the particles, how do we model them using formulations like Maxey-Riley-Gattignol equation? If the particles were experiencing thermal fluctuations, then we would be interested in Brownian motion. You will also be learning slender body theory, a very beautiful method to actually study highly anisotropic particles. You would be using these solutions to not just understand the dynamics of the particles, but also compute things of interest like effective viscosity or how they are going to cluster in the flow. By the end of the course, you will know how to not just analyze the individual particle dynamics and their motion, but you would be also in a position to do macroscopic continuum scale features from the problem. You can study about viscosity. You can also move into more advanced things like understanding how they can have non-Newtonian rheology. These ideas are underpinning modern microhydrodynamics approaches applied to microfluidics, environmental modeling, and biological transport. Microhydrodynamics connects phenomena that range from the birth of a raindrop to the swimming of a bacterium. It reveals the unity that exists between environmental flows, biological locomotion, and engineering suspension. So if you are interested in how the microscopic world moves and how those motions influence the macroscopic world that we live in, this course will be a beautiful introduction and give you the tools necessary to move forward in this. So welcome to this course on microhydrodynamics.